This is Neil from Anabit, and in this video tutorial, we're going to cover how to build a flexible power source circuit design for IoT and portable applications. And if you look at this IoT reference design here I have in this picture, this is Anabit's AIoT Sense node. The design we're going to cover is used on this reference design. So we'll use this as a demo so you can see that the design actually works and get to see it in action. Before I get started, I'll just mention check out anabit.co, where you can find open source data converter and IoT products like the AIoT Sense node. If you give us your email address, you can sign up for our newsletter to get updates on new products and new content like this video. All right, let's get started. So our flexible power source design is flexible. One of the reasons it's flexible is because it has three different power sources. So we can power it off of 5 volts, which for the Sense node is a USB-C connector, and that can power design. It can also charge our secondary power source, a lithium-ion battery cell or lithium polymer battery cell. That can serve as our second power source and can be charged from our first power source. And then our secondary charging input is our third power source. So this can be a lower power, not always there power source compared to the first bullet. And it could be a solar power, it could be an inductive wireless charging pad, or just some kind of general DC source. And what makes this different from the 5-volt input is the power for this could vary because it doesn't have to power the whole circuit, it just has to provide the battery with current. And that current might be enough to charge the battery and power the whole circuit, the whole design, I should say, or it might just be enough current to help reduce the load on the battery so we can extend battery life. For instance, if we're using a solar panel, the difference between having full sun versus shade, right? So the secondary charging source is really flexible because it doesn't have to be a constant power level. So what we're going to cover in this video, here's the agenda. We're going to go over a high-level circuit overview of our flexible power source design. Then we're going to see a demo of it in action using the AIoT Sense node. And then we're going to do a deeper dive into the circuit design, some of the circuit design elements of this and the PCB layout. All right, let's dive into the high-level circuit overview. Here is a high-level overview of the circuit design where I'm just showing some of the main parts and not the low-level capacitors and resistors and things like that. So all these blocks represent an IC, and I'm labeling what they are, and I also in parentheses are putting their part number. So let's talk about this design and how it works. So we have our 3 power inputs. We have the USB-C connector, we have the secondary charging port, which can go up to 7 volts, and we have our battery cell. Let's ignore the secondary charging source. Let's assume there's nothing connected there, and let's assume we have our USB-C power connected and our battery cell connected. In that case, the USB-C power source will forward bias this diode to power the DC to DC converter. And one thing I should mention is the output of this circuit is here. It's the output of the DC to DC converter, which is a regulated 5 volts that can be used to power the other parts of the design. I'm using it to power a 3.3 volt linear regulator, which is then used to power the ESP32. So this is the output, the main output of this design, this 5 volt regulated rail. So with our USB-C connector, we can forward bias this diode and power this DC to DC converter. We can also forward bias this diode to feed power to our battery charging IC, which is used to charge and regulate the battery cell. Lithium-ion batteries have a certain charge profile, and this battery charger IC makes sure that it follows the charge profile, and it also shuts off current when the battery is fully charged. Now, these diodes are basically for isolation, right, to keep the power sources separate. This power switch IC is also for isolation. So if you notice, there's a thing that says VDD control. So when VDD is present, this power switch is pulled high, or its control input is pulled high, and it's turned off or acts like an open, which cuts off the battery from the DC to DC converter and uses this source to power the design. So it isolates the battery and it can charge the battery. The reason I'm using this power switch IC and not a diode, because I could use a diode, is because diodes are not efficient, right? I'm going to waste power because I'm dropping voltage and current through that diode. And for my battery cell, I want to be as efficient as possible with how I use the battery cell. For this power source, I don't care as much about efficiency, right? Because this could be unlimited power. But for the battery, I do. So that's why I'm using the power switch, because it has a very low on resistance, and I don't waste power like I do with a diode. If I remove the USB connection and the 5-volt power, all of a sudden my power switch closes and the battery starts providing power to the DC to DC converter to power the design. And then, of course, these diodes isolate the battery from the USB-C connector so we don't have a live voltage there. Let's say we have a solar panel connected to our other charging source. Here we're using our switch. We're using two back-to-back P-channel MOSFETs. And the reason we're using two back-to-back ones, and I'm assuming you have a basic knowledge of MOSFETs, is because this way the body diodes of the MOSFET, which are part of the MOSFET, they face in opposite directions, so you can't forward bias them from this power source or this power source, so we can isolate things. Notice that this is VDD controlled too, so if the USB power is connected, these MOSFETs will act like an open switch. If it's not connected, it'll act like a closed switch, and this power source can come through. The USB, whenever it's connected, it is always the main power source. Let's say it's disconnected though, and we have a solar panel. Our switches are going to be closed, and I'll go over this circuit in more detail, and we'll get current flowing to the battery charger, which can then power the battery cell or charge the battery cell. And like I mentioned earlier, one of the beauties of this is if my solar panel is in full sun and it's putting out plenty of current, I can charge the battery and power the DC to DC converter and rest of the design. If the solar panel is, under some clouds and it's barely putting out any current, it just assists the battery in powering the rest of the circuit, so it helps extend the charge of the battery. So once again, this can be a variable power input. That's part of what makes this so powerful and so flexible. Then, of course, I have a battery monitoring circuit here where I can measure the charge or discharge current of the battery and the voltage. I have that connected to my microcontroller through I2C. I also have a logic level from the battery charger IC to know when the battery is being charged and when it's not. Another thing I'm not showing is on the DC to DC converter, for protection reasons, I have under voltage lockout. And so that way, if the battery voltage is too low, the DC to DC converter will shut off so it doesn't over discharge the battery. Of course, the battery charger IC is going to make sure the battery doesn't get charged too high. All right, let's take a look at this circuit in action, and then we'll do a deeper dive into some aspects of it. Okay, here we're looking at my patio. Here is the Anabit AIoT Sense node in the shade. There is the lithium-ion battery. This is a solar panel going into our secondary charging port, but it's turned upside down, so it's not providing any power right now. And then notice I have a USB-C connector that's connected to the design and providing power. We can see that the RGB LED is on. So let me start the demo video, and I'm going to zoom in a little bit. There we go. We can see the battery connection. And next I'm going to use an app to connect over Bluetooth to the device where we can read the battery state and the values. So we can see them printing out. And I'm going to pause it right there. So remember, we have the USB-C power that's going to power the circuit and charge the battery. I have the battery charging IC configured for a maximum charging current of just under 400 milliamps, which we can see right here. Notice this is negative, right? So that means it's charging the battery. If it's positive, it means the battery's discharging. So the battery's being charged with about 382 milliamps, and we can see it's charging. And we can see as we go down, it continues to charge at the same level because we're running off USB-C power. Now, let's see what happens when we disconnect the USB power. So I'm going to unplug the USB power. Circuit keeps running. And I'm going to connect my Bluetooth app to it again so we can see what the values are. Let me another printout. We'll do one more. So now we can see the battery current is no longer negative. It's 140 milliamps. And that's what it takes to power the circuit and the ESP32 and the RGB LED and things like that. So we can see the battery is now discharging, right? And if we go down here, I guess the voltage for the battery is pretty steady. Notice the voltage dropped pretty quick. That's because now the battery's under load. When the battery's not under load, its voltage jumps right back up. And of course, the voltage will slowly drop as it discharges. But the idea is we're just running off of battery power. Okay, now I'm going to turn over the solar panel. So now the solar panel is going to be exposed to the hot Grand Junction sun. And we have the battery and the solar panel now. So let's connect once again and check out what we see. So now we have the battery state is charging, and notice the current, it's at about negative 250 milliamps. So that means the battery's charging if it's negative current. And we can see the voltage slowly climb here. So we have a battery voltage at just under 4. Now it jumps to 4. So our battery is truly charging. Now, what you're not seeing is the solar panel is actually putting out more current than 250 milliamps because it's also putting out about 140 milliamps on top of this to power the circuit, right? So we're not seeing that current in this measurement, but the idea is the solar panel has enough to charge the battery and power the circuit. If I were to cover the solar panel, which I'm not going to do in this demo, what would happen is we'd see that this charge current drop and possibly go positive if the battery has to help power the circuit along with solar panel. All right, so that's a demo of our circuit in action using Anabit's AIoT Sense node. Let's do a deeper dive into some of the circuit elements. Okay, here we're looking at my PCB layout software in Fusion 360. And first, I'm going to start with the USB-C connector. Now note, not all these circuits are on a continuous schematic, so I'll jump from one page to the next. But the idea is this is the USB-C connector where our 5-volt power comes in. Notice I gave it the same name, VDD, on this node. And these are the same diodes we saw in the high-level circuit diagram, right? So this diode, if it's forward bias, goes to the input of the DC to DC converter, which I'm calling that bus VCC. And this diode, when it's forward bias, goes to the charge input of the battery charging IC. Now, one important thing to note here is this resistor. I didn't show this in the high-level circuit diagram, is if we don't have the USB-C power connected, these diodes can have some leakage and it can make it appear that there's a voltage on this node, which we don't want because that node either being high or low controls some of our switching. So I need to make sure I pull down this node so that when there's no USB-C connector, that this is a true almost 0 volts here. Okay, here's where a lot of our power circuits are. So over here is my battery charging IC or battery management IC. This is the charge power. So this is where that diode we just saw on the last slide, the output of it connects. And then here's our back-to-back P-channel MOSFETs, right? So P gate is connected to the gate of the MOSFET, S is source, D is drain. P gate also connects here wherever you see the same name, the nodes are connected. And I'm using 2 N-channel MOSFETs to turn them on and off based on whether solar power or any type of power is present or VDD is present. So notice VDD, so this is coming from the USB-C connector. If VDD is present, this N-channel MOSFET turns on, pulls this low, turns this one off. So then the gate of the P-channel MOSFET is at the same voltage potential as this source, which turns those P-channel MOSFETs off or makes them act like an open switch. If there is no VDD, this gate is pulled high, which turns it on, which ties the P-channel MOSFET gates to low. So they're going to be a lower voltage than the source, which turns them on or makes them act like a closed switch. And then it can feed power into the battery charger. And then the output of the battery charger, BAT SR, connects to a shunt resistor that we use to measure the current to the battery, and that shunt resistor then connects directly to the battery. So the battery is essentially here at this node, but with a small value shunt resistor in there as well. Here is the power switch, right? So this is between the battery and VCC or the DC to DC converter. And so you can see BAT SR, V in, and V out is VCC, which connects to the DC to DC converter input. And then if VDD is present, that makes this battery or this power switch act like an open. And if it's not present, we want to use battery power, it's pulled low, and so it closes that switch or turns it on to power the DC to DC converter. Up here is the DC to DC converter. You can see the input VCC, the output is 5 volts to power the rest of the design. I'm not going to go into detail on how to configure the DC to DC converter. That's a separate video. And in fact, we have a video on that from our partner company, Forcetronics. I'll provide a link. So if you want to know how to lay this out and choose all these component values, I'll put a link to that video in the video description. The last thing I'm going to mention, I'm not going to go over this in detail, but this is the chip I'm using to monitor the battery. So we have a shunt resistor that measures the current. It's connected to the battery and to the BAT SR or BAT shunt resistor node. So that way I can measure current in either direction. So negative current was charging the battery and positive current is the battery is discharging. And then this chip also monitors the battery voltage. so we can keep an eye on the battery and what's happening. Here you have the Anabit AIoT Sense Node layout. So this is the layout of the schematic circuits we just looked at. This is USB-C connector. This is the input for the charging source, and this is the connector for the battery. You can also use these pins. This is a high efficiency DC to DC converter IC. So it means it has a fast switching rate, which means it can sometimes be tough to lay out because it can become unstable if you have too many parasitics in there. And so I have these nice wide traces with my components real close to the IC. So I reduce parasitic inductance so this chip runs smoothly with high efficiency. Here's my back-to-back P-channel MOSFETs for the other power inputs. Here's the battery charging IC. Here's my battery connection, right? I want this to be efficient. That's why I have wide traces. And then here's my cutoff switch, real small IC. All right, that's it for flexible power source circuit design for IoT and portable applications. If you're interested in test driving the circuit, or if you need some type of open source reference design AIoT platform, check out Anabit's Sense Node at anabit.co. If you like what you see here, please hit the thumbs up. If you have any questions, use the comment section of the video. And thank you for watching.